Good morning, ladies and gentlemen. May I have your attention, please? Thank you. And so today we'll have an opportunity to review some of the material that you've been learning over the course of Unit 1, Functions. But firstly, let's remind you about solving multiple step equations. And so in number 1, we've got an equation involving fractions. Number 2, we're going to reverse and undo to solve for a variable in a formula. And then number 3, we'll have an opportunity to deal with some multiple solutions. So make sure on your test that you're on the lookout for those equations that might have more than one solution, right? More than one solution. And lastly, we'll do a piecewise defined function to make sure you're good to go with day 9's material. Okay, at this time, raise your hand if you did not get red mark for today, the 29th. Is everybody good? This will be your last of 10 red marks. It'll be counted, right, as part of your Bellwork from Unit 1, and they'll be combined with your activity stamps to get a total later in today's class period. Firstly, recall that we can clear the fractions when we have multiple denominators with the same problem in one fell swoop if we multiply each term by the least common denominator. So go ahead and share with the class when I call on you, what's the least common denominator, given that there's 3 different denominators in this equation? So what's the least common denominator? Tyler?
12.
12, great. And so we're not going to make common denominators on each of those fractions. We're going to multiply everything by the number 12. And that's what's going to clear the fractions, right? Not keep the fractions. We want to clear the fractions. Thank you. So we'll multiply everything by 12. And when we do that, we'll go term by term. So it'll be 12 over 1 times 2x over 3 minus 12 over 1 times 7x minus 4, or over 4 rather, plus 12 over 1 times 3 equals 12 over 1 times 3x over 2. So notice how we've taken everything, every term on both sides, and we multiplied it by 12, right, our least common denominator. Watch what happens when we do that. We can reduce first or reduce second, right? If we do 12 times 2x over 3, I get 4 times 2x is I get 8x. No fractions. I love it. 12 over 4 is 3 times 7 is 21x. No fractions. Plus 12 times 3 is 36. Equals 12 over 2 is 6 times 3 is 18x. What I like about the blue line, right, that's different than the original? No fractions. So our technique to clear the fractions in one fell swoop is to multiply each term on both sides by the least common denominator. Now it's just a hop, skip, and a jump, right, away from the answer. We know we can combine like terms, same side, same operation. So it looks like negative, is that 13? X plus 36 equals 18x. And then it looks like you can add 13x to both sides. And I get 18 plus 13 is 31x. And then finish it out by, $30, watch where that lands. Finish it out by a division. We can divide both sides by 31. So my final answer is x equals 36/31. And go ahead and leave that as an improper fraction. Fully reduced, 31 is prime, and so we won't be able to reduce this fraction and divide out any common factors on top and on bottom. Awesome. Did anybody get all the way to 36/31? We tried to put some tricky ones on the last day for review, okay? Good. If you didn't, that's fine. Go ahead and take a minute. And you can make corrections, or you can check this out on the PDF file, or post the notes, or listen to the recording. All right, let's go ahead and take a look at the second. Here we're going to rewrite a formula for a particular variable. So if we wanted to solve for x sub 2, I'm going to go to the side where x sub 2 is. X sub 2 is hiding right here. It's hiding right here. Is it on the bottom of a fraction? No, thank goodness, right? Are there more than one x sub 2 term? No, and so I'm all ready to go with my forward steps and then reverse and undo to get my solving steps. So let's go ahead and practice. I know that if I were to cover up the equation and just focus on the expression side that contained x sub 2, the variable I want to solve for, then I could list my forward steps by pretending I was doing a middle school evaluation problem. In other words, if I were to plug in something for x sub 2 and evaluate this whole side, what order of operations would I use? Well, first I plug in something for the underlined x sub 2, then I would subtract x sub 1 first. So subtract x sub 1 is my first forward step. Then I would square it. I'll write that shorthand raised to the second power. Then I would increase that value by the quantity y sub 2 minus y sub 1 all squared. And finally, I would take the square root. Do I need a plus and minus here? No, the radical is already present. I'm not creating the radical to undo a squaring. I'm not solving a squaring equation, right? I'm not undoing a squaring here. I'm simply stating what the forward step was, and there was already radical, so there's only one radical here. Now I'll go ahead and reverse and undo to get my solving step. So here we go. If the last thing I did was take the square root, the first thing I'll do is square both sides. Then I'll decrease it by the value of that quantity. So I'm going to subtract that big quantity y sub 2 minus y sub 1 all squared. Then I'm going to undo that squaring. What undoes the squaring? Well, square rooting. And now's when I need the plus and minus. If I'm undoing a squaring, right, as an inverse operation to solve, that's when we create the positive and negative square root. So to undo squaring, I can do the positive and negative square root. And lastly, what undoes subtraction by x sub 1? Oh, I know, addition by x sub 1. So let's go ahead and apply our solving steps in order. First thing, square both sides. So we're going to square both sides. What does that do for us? It gets rid of that big long radical. So I get d squared equals x sub 2 minus x sub 1 quantity squared plus quantity y sub 2 minus y sub 1 quantity squared. Next step, I'm going to subtract y sub 2 minus y sub 1 quantity squared from both sides. So next step, subtract that. I get d squared minus y sub 2 minus y sub 1 quantity squared equals, and on the right hand side I've got x sub 2 minus x sub 1 quantity squared. Next is my third solving step. Do the positive and negative square root. So that undoes the squaring. So I know that the positive and negative square root of d squared minus y sub 2 minus y sub 1 quantity squared equals x sub 2 minus x sub 1. Which means that we're simply one step to go. Yes, that's right. I go to my last solving step, and all that remains is to add x sub 1 to both sides. So my final answer is going to be x sub 2 equals x sub 1, that's positive, plus or minus the square root of d squared minus y sub 2, that should be, minus y sub 1 squared inside close bracket. This should have been y sub 2 right there. You could have put the positive and negative radical term first and then plus x sub 1. That's equivalent so long as the signs match. I chose to put the positive x sub 1 first because it's good math manners to have. It's good math manners then to have that plus or minus in between, but it doesn't matter in terms of your accuracy. Wow! That was a rip-roaring problem to start your Tuesday/Monday day. What questions do you have about number 2? No? Me? All right, let's go ahead and box that bad boy. And then we'll go to our third one. Recall that absolute value equations, right, have the potential for more than one solution. How do we find them? Well, first we want to add or subtract, multiply or divide to get the bars alone on one side. As I scan this problem, are my bars already alone on one side, Luke?
Yeah.
Yeah, so I don't need to do any preliminary steps before my breakup, right? Before my breakup, I'm ready to go with my breakup. We can also do our strategy again. So if there's a single variable on one side, not on the bottom of a fraction, I'm ready to do my forward step. So I'll cover up the equation. I'll focus on the expression side, plug in something for p. The first thing I would do in forward steps would be times by 2, then minus 3, then take the absolute value. All right, let's reverse and undo. My favorite undoing absolute value bar is break it up. I'm going to break it up and rewrite what that starts. So break it up. Next, undo subtraction by 3. I got it. That's addition by 3. And lastly, undo multiplication by 2. That's division by 2. Here we go. Break it up. Break it up. And so I'm going to go ahead and set my quantity inside the bars equal to two separate, right? Two separate numbers, two separate distance numbers. So I look at this and I say absolute value means the distance between that quantity back to 0 on the number line. What two numbers are a distance of 11 units on the number line away from 0? Well, positive 11 and negative 11. So that's how I break up the bars. I set whatever's inside, in this case 2p minus 3, I set it equal to the positive distance number, and I set it equal to the negative distance number. How come? Because those are the two numbers that are a distance of 11 units away from 0 on the number line. So I get two equations. That's my breakup. That's my break it up. And now we'll go ahead and continue on, add 3 to both sides of each equation, and that's where my paths split. Pretty sweet. Guess you could say that's pretty sweet. Divide both sides by 2 to finish it out. Dirty dog. And I get p equals 7 and p equals -4. But before I box it, same on my test, I'm going to go ahead and take that potential solution value for p, plug it back in the original, and make sure it satisfies, makes a true statement. Then I know it's a correct answer, right? So I'm going to grab the negative one, because they're pesky little buggers. -4 and for p, 2 times -4, I can even use my green steps. -4 times 2 is -8, minus 3 is -11. Absolute value of -11 is 11. It makes a true statement. So I know that I'm correct, and I'll box it. If I were to quick try 7, 7 times 2, 14. Minus 3, 11. Absolute value of 11 is still 11. And so both of these satisfy the original. I'm confident in my solutions. I'm ready to move on. What questions do you guys have about number 3? Awesome. Okay, now let's take a look at Unit 1, Day 9's material. That's when we had our piecewise defined graphs. And so suppose that we had three different pieces in this particular graph. Recall that we need two things, right? We need two things in order to write the equation of a piecewise defined function. We need the equation of each curve, right? Each piece. And we need the domain restriction to tell the viewer where that function rule applies. And so we got this particular windows of x values for which a given function rule produces the picture. Let's go ahead and take a look at the red picture. So the red picture here could be written a couple different ways. Some of you might choose to use part of the absolute value function, right? You might use the absolute value function for that portion. Some of you might use -x because it's a downward sloping line, right? A downward sloping line with negative slope. And so either one is fine. Because we used -x a lot on the previous day, I'm going to go ahead and do -x. And that only applies when x is to the left of or equal to, because of the filled-in circle, -2. So by rewriting that as -x, that picture in red is only produced if we're looking to the left of or equal to -2. Next up, the blue graph. The blue graph is my cubing function, right? My cubing function is that snake-like shape, the snake-shaped graph that changes curvature there at the origin. That blue equation is given by y equals x cubed. However, in this picture, it only applies when x is between -2 up until +2. Oops. Because -2, right, and x equals -2, this picture has an open circle, then it has to be a strictly on my inequality symbol. At x equals +2, it's a filled-in circle. Therefore, I must have it or equal to on the +2. Does everybody see the difference in these boundary values? So less than, right, versus less than or equal to. Open circle versus closed circle. And when we go, it looks as though the final portion of the graph is given by a constant function, y equals a number. In this case, y equals -3. Whenever x is to the right of +2, then the output value, the y value, the green coordinates, right, the green points, have a y value of -3. Awesome. All right. So domain restrictions aside, go ahead and raise your hand if you had the function equations right. You had the piece equations right? You had the piece equations right? Good. Raise your hand if you had the domain pieces right. Did you have the domain pieces right? Good job. If you didn't, then let's go ahead and fix those because this is a great one to review before your test. It's a great problem to review before your test. Awesome. Okay, so let's go ahead and do our homework check. We do need the stapler today, so we've got a two-part assignment. Our two-part assignment is going to include, right, our piecewise defined function graph. We're going to put that on top. And then our day 9 practice, functions practice, that's the please match the letter, the multiple choice matching. You're going to staple that on bottom. So we want our piecewise on top. Katie and Margot, if you'd start that stapler. Erica and Olivia, if you kindly start the stapler. Please be ready for the stapler when you receive it, and staple your piecewise on top. So piecewise function goes on top of your day 9 practice. Go ahead and give yourself credit while you're waiting for the stapler. Give yourself credit out of 40 total problems. Out of 40 total problems, no reading question. Divide, enter, multiply by 4. And then box your infinite campus score round to the nearest half point 0 to 4. So it's out of 40 problems. Make sure that your name's on the name blank there on top. And then we'll go ahead and check for accuracy. Remember, you're still waiting for the staple, and that's fine, but be ready. We're going to go ahead and check our answers now. There's more than one answer for a lot of these. So you could have used the absolute value function. We did the first two together, so we'll pick up with number 3. In number 3, the left side is given by the reciprocal function, 1 over x. The right side is given by the identity function, y equals x. The domain restrictions must be strictly on the reciprocal. The left one is reciprocal for number 3. Bottom of the page. Number 4, I broke up into 3 pieces, negative x, x, and negative x. Number 5, 2 pieces, the inverse squaring, and the square root function. The inverse squaring must be strictly, bless you, the inverse squaring must be strictly. Yep. Did you do 1 over x?
I did the opposite.
Okay, so yes, that makes a branch. However, notice how this portion of the branch is closer down to the x-axis than the corresponding piece right here on the y-axis. That's an indication that it's inverse squaring. If it were the reciprocal function, they'd be equidistant, so they'd be symmetrical. It'd be the same distance here as it would be here as you look up and down, so that's kind of how I tell the difference if I'm just given a graph. Great question, though. And 6, 3 pieces, negative 2, x cubed, and positive 2. You guys have like bigger circles on there, so you can tell which is going to be the closed versus which is going to be the open. What questions do you have on graph to equation? Graph to equation? Then please know you'll have to go from graph to equation and equation to graph. So how do we do equation to graph? Well, let's take a look at 7. And number 7, absolute value of x is a v. So the opposite of absolute value of x is an upside down v. That portion is shown in green as it only applies when we're looking to the left of or equal to negative 2. My middle section is an upside down parabola. My upside down parabola I've shown in blue, and that only applies in between negative 2 and 1. Pay attention to open versus closed. Lastly, positive x, the identity function, produces the function's graph only if I'm looking to the right of x equals 1. Number 8, absolute value of x is a v. The cubing function is my snake-like graph that changes curvature at the origin. And negative x then will be the negatively sloped line, the opposite of the identity function. Please note, you could have used negative x for the blue graph as well. Is that's still a negatively sloped line, right? If you were going the other direction. But here you were given absolute value of x and making its picture. Right? You were given the equation and making its picture, not the other way around like the first thing. What questions do you have on the equation to graph? Then let's check our matching. Everybody, let's check our matching. Please write the letter of the equation in the space provided. Get ready. We'll go in order left, right. Slide 1. D, decimal. A, algebra. B, binomial. C, calculator. For absolute value. Slide 2. A, C, D, B. For the parabolas.
No words?
Yeah, I know, it's tough. You have to look also. Look and listen. Multitasking on a Tuesday, like a Monday. Third slide, B, C, D, A. Followed by D, C, A, B. Followed by cubing function, C, D, A, B. That's pretty sweet. And the inverse squaring function, D, A, C, B. Absolute value, D, A, B, C. Now it's time to do our graphing. And so we're going to carefully sketch a graph of the parent and then the new function. How does the new function compare? Well, notice the 3 multiplier makes the y coordinates 3 times as tall for a given input. No longer do we have the key point 1, 1. We now have 1, 3. The y coordinate is 3 times as tall. No longer do we have the point 2, 2. We'll have 2, 6. The y coordinate is 3 times as tall. And so you can get key points by multiplying the y coordinates of each key integer point by 3 before plotting them. 3 times as tall, the arms are 3 times as steep. 1 over x, opposite of 1 over x, we just flip the orientation top to bottom. Opposite orientation, that's reflected over the x-axis. Same key points, right? A rigid transformation, reflection across the x-axis. The square root of x, the negative makes it upside down, or reflection over the x-axis. The 2 makes it twice as tall. So twice as tall y coordinates. Twice as tall for the y coordinates, and then the negative makes it a reflection across the x-axis. X cubed, the 1/2 makes the y coordinates half as tall for a given input. And so instead of having the key point 1, 1, it's going to be 1, 1/2. Instead of having the key point 2, 8, it will have 2, 4, half of 8. And that's how I can get key points. It's only half as tall. All right, so go ahead and give yourself an accuracy fraction on top of the piecewise out of 40 for the whole assignment number 9. About how well did you do? In pen, circle that. Make sure your Infinite Campus score is boxed in pencil, nice and big, and that your name is on your packet. Anybody else need a stapler? Staplers? Put them back. Thank you. Where's the metal stapler? Thanks. Pass it in. Or can you pass it to the side? You can pass it, Braden. Thank you. Thank you, Braden. Go ahead and pass them in from the back to the front, please. Front rowers, make sure they're facing the same direction. I appreciate your help. Everybody good with number 9 if you did it? Number 9? Yes.
I have this one from last class.
Yes.
Because I'm sick.
Wonderful, thank you. So just put absent on time on top. I got it. Okay, ladies and gentlemen, now it's that moment you've been waiting for. How could you make it through the weekend, right? When you had an extra day waiting in agony for function calisthenics. And so yes, in just a moment we're going to do function calisthenics. We have a procedure from last time that we employed. I'm going to pause the recording and then move the microphone so it doesn't get bumped. But first I want to go ahead and show you how we're going to do our new pictures. And so we're going to do some new pictures. We can stay in our seat for the beginning part and then we'll get up and go after we set up our new pictures. What do you mean new pictures? I'll tell you. Here we've got the hyperbola function. So we're going to show that. We're going to show that with our hands. So with our hands, we're going to model the behavior of the reciprocal function, which is a hyperbola. If k is positive, recall our orientation. Our orientation was in the diagonal quadrants 1 and 3. So for positive k values, our orientation is 1 and 3 for the quadrant numbers. Negative k values, right? Negative k values are going to make those orientation opposite. And so you'll flip across the x-axis, and now it'll be quadrants 2 and 4. So quadrants 2 and 4 are where my reciprocal function would appear for negative k values. Recall that absolute value of k greater than 1, that just means big k values, either positive or negative. That's going to make it farther away from the origin, right? So that's when your y-coordinates get taller. Now you'd be farther away from the origin, either positively or negatively for k. And small values of k are going to make it scrunch down in. So you'd be closer to the origin, shorter y-coordinates if you had small values of k. For inverse squaring graphs, that was our Atari symbol. So positive k value was up, up. Positive k value was up, up.
Good morning. At this time, please send the juniors and seniors to the PAC for the assembly. Freshmen and sophomores, you will continue to follow the normal morning bell schedule for first and second period. Again, at this time, juniors and seniors may report or should report to the PAC for an assembly. Thank you.
Negative k values are going to take that quadrant 1 and 2 and jump it down to the bottom, right? Now it's going to be quadrants 3 and 4. And so 1 and 2 quadrant orientation is going to reflect across the x-axis and now become quadrants 3 and 4, right? We're going to show that with our palms by doing down, down. Okay, so we're going to just show the placement, the quadrant placement of the graphs based on positive versus negative values. Okay, so in general, what effect does k have on the graph of kx? K positive means we're increasing behavior, same direction as my parent function.
One more quick reminder, juniors and seniors, when you do enter the PAC, if you could please be seated in the front half of the PAC. We'd appreciate that as well. Get yourself settled and ready to go. Thank you.
Large values of k correspond to a very steep graph, and you showed that with your arms very well on Thursday. And then negative values, right? Negative values of k, but large negative values is still very steep. It's just now top right hand is up high, right? Versus small values of k, more gradual. You're going to be closer to the x-axis, shorter y-coordinates. Kx squared, k positive, right side up, bowl shape, total bowl shape. Versus negative k values, upside down. So upside down bowl shapes. Absolute value of k is large, going to be taller y-coordinates, steeper arms versus absolute value of k smaller. Now we're talking about shorter y-coordinates, less steep arms. Awesome. All right, and now it's time for your favorite game. Yes, that's right, function calisthenics. And so we're going to go ahead and now get up around the room. I'm going to pause the recording so we don't hit the microphone. Okay, ladies and gentlemen, thanks for your participation in function calisthenics. And so, here we have our Unit 1 quiz reflection. As an advanced algebra team, we sat down and we looked at collectively, based on our 11 sections of advanced algebra, what were some common mistakes that were made on the Unit 1 quiz, And let's now make a couple examples so that we can correct those. Let's fix those before your Unit 1 test, right? So that you guys do better on your Unit 1 test than you did on your quiz. And so while some of these are some algebra stuff that we'll run into throughout the course of the year, there are two that were specific content objectives from this unit, and they're shown with asterisks. And so we're going to focus on these three in the middle here. We're going to find a function value, a y value from a table. We're going to find a function value from a graph, and then we're going to practice with domain and range, whether we're looking at a table or a graph. And so everybody, we made up these examples after we already completed the note sheet as a basis of our quiz reflection. So what I want to do now is go ahead and take a look at these examples. There's no space, but there's room on your landscape. On the back, there's some room. On the right-hand side, just look at the table. And we want to remind you about some key things. And so on your regular note sheet, just find some space on those back problems. On the right-hand side, there's a little bit of space there. We made up these problems to help you avoid some mistakes that were made up in Unit 1 quiz. Let's take a look. State the domain. Everybody go ahead and be ready to tell me our domain values, my k values, or my h of k values when I call on you. So which one is the domain values? Is it the k values or the h of k values based on this table? Which one are the domains? Carson?
-2, 0, 3, 11, 17, and 18.
Absolutely, right? The input values, generally the top row of a table or the first column in a T-chart are the independent variable values. In this case, the k values. Perfect, thank you. And so we can list those. If we're given a table, then it's just a list of numbers with commas between them. And so you could say the set of all k such that, or you can just list them in a set, like we did in class when we were doing Robert Wadlow and his age. So -2, 0, 3, 11, 17, and 18. Recall, it's good math manners if you list these in increasing order. My table already had them in increasing order. If they were out of order, I would list them in increasing order for good math manners. The range, then, is the set of all outputs. And so the set of all outputs, right? If there's repeats, I don't need to list them more than once. Telling somebody that 86 is a member of the outputs means that 86 is an output that's produced. We don't have to say it every single time it's produced. So we'll simply list our output values, our h of k values, in increasing order. So my least to be -16, followed by -4, followed by -2, followed by 4, followed by 86. Notice how I'm only listing 86 once. Does everybody see it? And lastly, h of -2. So h of -2, right? Is h of -2 going to be -16 or is it going to be 3? And how do we tell? Well, recall, inside the parentheses is my input value. So I'm looking to figure out the value of h when my input k is -2, which means I'm not looking at this point. I want the input value of -2 and see what function value h it's paired with. So I'm looking at this order pair, which means this equals -16. You see that? H of -2 equals -16. It's that point. A lot of people on the quiz picked something like this and put 3. Okay? Don't do that on the test. Do you see the difference? You want the function value that corresponds to an input of -2. You guys see that? Okay. Lastly, we wanted to provide the same kinds of questions, but now with a graph, a continuous graph. And so now, while it was okay to list individual values when we had a table, a finite number of values in my domain, here we have an infinite number of values in my domain, an infinite number of xi's. And so here we're going to show that by using that inequality notation in set token. So how do we do that? We'll say the set of all x values such that, and now I go to the leftmost side of my x window. So along the x-axis, the leftmost side of my picture is that x equals -6. And so -6 is the left side of my window, which is less than or equal to x, which is less than or equal to my right side of my window. So we'll go all the way to our right side. What's the greatest x value for which a picture is produced? Looks like 7 is the greatest x value for which a picture is produced. That's not to be confused with the range. The range of my graph is the collection of all y coordinates, outputs, function values that are produced, right? And it looks to me like my least function value that's produced is not -6, it's it's not 7, it's -3. It comes from this bottom point right here. And so the set of all y such that -3 is less than or equal to y is less than or equal to, and now what's the greatest y value produced? The greatest y value produced is what? You can call out 6, and so 6 would be my topmost y value, and that would end my set builder notation. So everybody see the domain and range? What's the difference between these inequalities here and the commas? A finite number of inputs, a finite number of outputs. We had a table, so we'll list values. Here we had a continuous graph, right? And so a continuous graph will go ahead and do a range of values, right? A whole infinite number of values. Great. And lastly, estimate h of -3. We can estimate it by spitting out the y coordinate that corresponds to an input value, an x coordinate of -3. So we're not looking here, we're looking along the x-axis to see when x equals -3, what is y about? It looks like y is about 2. So remember, you're stating the y coordinate that corresponds to an input of -3. You guys see that? That was something that people missed out on the quiz as well. Hopefully, by looking at these types of questions, right, if you made mistakes like that in your quiz, now you won't make mistakes like that on your Unit 1 test and you'll do a little bit better. So that's our goal. All right, so we need a stamp count. What we're going to do is we're going to count up the number of stamps that you've earned throughout the course of the year. I'm sorry, the unit rather. Wait, don't do it just yet. I want to outline the assignment first. So the assignment, the Unit 1 review assignment, bless you, is printed out on that last page of your note sheet. There's a whole bunch of problems here taken from different sections of reviews and self-tests. And there's a solving equations worksheet. Solving equations with multiple solutions, because that's some place where students forgot on the quiz. The multiple solutions, some people forgot the plus or minus or how to break up bars. So altogether, there's about 80 problems on this review assignment. However, to get full credit on your review, you only have to pick any 40 or more, right? So you can do any 40 of those. What I recommend doing is tailoring your review, right, based on your individual strengths and weaknesses. So maybe Braden wants to practice with multiple solutions. He's going to do all of the worksheet and then just pick several from in here to get to his 40. Maybe Luke feels good about multiple solutions, but he wants to practice with his domain and range. And so he's going to spend more time figuring out the domain and range problems that are from one of those individual sections. Either way, I hope that you preview all the problems first and then decide how to best spend your time. Don't just do the first 40. That's not going to do you any good, right? I mean, unless those first 40 include ones that you need practice with. Instead, maximize your review potential by purposely selecting those that you are bad at and need to practice with. That way you can tailor this review to fit your individual strengths and your individual weaknesses, okay? Now let's go ahead, and you're going to have the rest of the time to work on that quietly. You may work with another person so long as you're on task, right? And you're quiet, and we'll turn that to the next time. Margot? Yeah, but just put it back when you're done. First, what's that?
I just have those books that
Yeah.
we just
Yeah, and then put it back when you're done. Don't take it. Okay, ladies and gentlemen, at this time I ask that you take a look at where we can earn stamps during this unit. Unit 1, day 1 through day 10, Bellwork include a total of 10 red marks possible. If you were gone and you never completed the Bellwork, then you might have less than that. You need to find your red marks and count up how many red marks you have from the note sheets for Bellwork. Next, the activity stamps. The blue activity stamps came from a variety of different places. We had our solving equations out of 4, our building functions worksheet, number 5 and number 10. On the back, rewriting formulas worksheet, number 4 and number 7, a total of 2. Our squaring functions activity was 2 stamps, and then our reciprocal and inverse squaring was 3 stamps. We had 4 and matching, and then we had 4 and 8 and matching for the last one, for a total of 13 blue stamps altogether. What you're going to do is find all your red marks, find all your activity stamps, and total them together as a single number. We're going to write that total down on your review assignment or your note sheet or your binder or your forehead or your palm somewhere, and you're going to give me that number when I walk around the room. So the total here is going to be out of 23. You're going to get a single number based on the number of red marks and activity stamps you earned throughout the course of Unit 1. Questions about how to get that total? do that count first, please. Write down that single number on your note sheet or your assignment page, and then I'll come around and conference with you individually during work time to get that total, and so I can record it and put it in Infinite Campus. Thank you for getting your total first and working quietly. I'll go ahead and stop the recording now.